Hi everybody, sorry about the delay. It's been a day or two of a lot of baby stuff, but baby's at daycare, so I'm ready to do some recording. So I'm going to talk about the last roughly 2/5, 1/3 of the class, everything that came after the midterm. And I'm going to start by talking about logistic regression and classification. And this is the trickiest topic of this latter part of the semester, and I'll start by reminding you where we left off right before the midterm. So there was this problem known as regression, where we have a bunch of data and we extract some features from the data, and we end up in this big d-dimensional space. And then using those features, we then, for each, say, row in our table, we are going to predict a single number that will be, I don't know, for example, the height of a particular person given their gender, zip code, whatever else, right? So you know the regression problem, hopefully. And in particular, we said that the ultimate goal, if we think about it in a mathematically rigorous way, of the regression problem is we want to find the theta that minimizes this expression. So this expression here, this is the squared loss. So if we're using the L2 loss for regression, this is the squared loss we're trying to minimize. And we also want to minimize the complexity of our model using regularization. So that was the framework, what we were trying to do with regression. And I don't have it here on the slide, but we found that the equation that solves this without the regularization is the normal equation. And once you add the regularization, it's just a slight tweak on the normal equation, assuming that we're using a linear model. Okay, so that's regression. So now we come to classification. So it's very close in terms of problems. We still have a bunch of data, we still extract features in a big d-dimensional space, but now we want to not decide a number, but a label. So for example, whether or not you are alive, or if you're a cat, or if you're a dog. And this could be either a binary classification, like a yes-no question, or it could be multi-class, though we restricted our discussion primarily to binary classification because you can solve multi-class classification problems by building a bunch of different binary classifiers. So then the really hard math for the classification problem was to try and figure out what's the equivalent expression that we had for regression for this classification problem. So one way that we could approach this, as you may remember from the lecture, is let's just use regression like before. We're just going to use let's say a linear model with the L2 loss, and then it would just be the normal equation. And we'd end up here with our least squares estimate. And let me tell you a little bit about this data, just to remind you. This is two classes of data. These are all of the items that are in class 0, all of the items in class 1, and the fact that they're not all exactly on the line is just because we've added some jitter to avoid overplotting. And so if we did the standard regression here, we would be drawing a best fit line that is a little bit strange, where, but it does make some intuitive sense that this is an item which has a value of, say, this right here, it has a value in our regression prediction of like minus 0.1. And so that seems like, okay, we'll call that class 0, right? So everything to the left of some arbitrary line, we would call everything in class 0. And everything to the right of some point, probably at the 0.5 mark, we would call that our class 1. And that's one way we could try and solve the classification problem. And so this picture here from lecture is exactly that. It says, okay, how do we actually use this? Because if we think about what we got back out, we're getting a number back from our regression, but we want a class. And so the natural thing to do is just threshold the number, and that gives us our class. Okay. And so that there, it works. It does something. It is actually a classifier, and you can see that it does a fairly decent job, right? All of these items are correctly classified. All of these are correctly classified. So it's much better than just flipping a coin. Now, there's some serious issues with this technique, principally that it is extremely sensitive to outliers. So if I add just a single extreme point, one data point which has a value of 100 here, this was size in the original example from lecture. So if we have a single data point, this is like a clump of cells of size 100, well, it suddenly skews our regression extremely strongly. And so instead of having a regression line that does a pretty good job, the original gray one, now we have this new regression line that is just terrible. It's a very, very bad classifier. Okay? And in particular, we say that the decision boundary, the point where this crosses the 0.5 mark, it is moved quite a lot just by this single data point, right? Now, it still does an okay job, I guess I should say, right? So it's still getting all these right. But if you were to put an even more extreme data point, you get an even sharper slope. And this just illustrates intuitively what's not so great about this, okay? All right, so how do we fix it? Well, there were two changes we made, right? So instead of just doing a regular linear regression, we first said instead of having our model output a line, basically, that is linearly dependent on our features and on our parameters, we're instead going to have it be shaped like a logistic curve, like this. So that for extremely small values, it is 0, and for extremely large values, we get back 1. And I'll give a little example of this shortly, but that's one of the big differences. And then the other thing we did is that we minimized the KL divergence instead of the L2 loss. And we'll talk about why that is as well. And these are the two big differences from the regression-based analysis. So what is the logistic curve? Well, recall that it basically, our usual linear model says let's take our features and compute the dot product with our theta, and that gives us our regression, right? That's the way we compute the value. And all the logistic curve is applying a function sigma to that value, right? So this is that value. And we get back 1 over 1 plus e to the minus regression value, we might call it. And that right there, that's what our logistic curve, like this shape here is exactly this expression. So how do we interpret that? Well, we think about it as the probability, given this set of parameters, that our particular current data point, that it belongs to class 1. In other words, if we look at this curve here, if we're way over here, we're saying the probability that it's in class 1 is near 1, and for way over here, the probability is near 0. So this is a probability value, and one of the reasons that we have a logistic curve is the fact that it goes between 0 and 1, which, hey, probabilities. Okay. And so we can think about this as the probability that x belongs to class 1. And so as an example, just to make this very concrete, let's imagine that each row of our table is of our table is about restaurant information, right? Kind of like our tips data set. And let's say we want to predict whether or not the current group, the current people dining are on a first date or not. Okay? And let's say we have two features. We have the length of the meal and we have the total bill. Okay. So phi 1 is the length of the meal, and phi 2 is the total bill. Okay. There's a strange, here we go. All right. So then let's suppose that our model has theta 1 as 0.006 and theta 2 is 0.003, and that for a given table it was a 30-minute long meal that they paid $44. Well, in that case, if we just compute the dot product here, we get you get this value, which is 0.312, and we negate it because we're going to ultimately put it through, sorry. The value we get back is 0.312, so that is phi transpose theta. And when we actually plug this into our logistic curve equation, then we get 1 over 1 plus e to the minus 0.312, or 57.7%. So that's what our model does. Okay. In fact, all right, so let's play around with this just a little bit, because I think you might find this interesting. Let's say that instead our diners, let's do 1 over 1 plus e to the, okay, so this is my 57%. So if I start saying, well, maybe the diner spent 100 minutes, well, now it's 67%. 200 minutes, 79%, and so forth. So that's what our model is actually doing. If our diners left in 0 minutes and spent no money, then it's 50%. And that basically is just that if we have a value for our regression of 0, of course, our estimate is 50%. Now, if you want to actually have the model give a different prediction than 50% whenever you're at the value 0, all you need to do is add a bias term. So that is, you'll have a third theta that is just an offset. And as you may recall from lecture, that just shifts the logistic curve around. Okay? All right, so that's what a logistic model actually does. Given the theta and phi values like this, we get predictions about whether or not we belong to a certain class. Okay. Now, how do we know the quality of our predictions? Well, we could use the L2 loss, but what we usually use is the KL divergence. Okay? So I'm going to present this just slightly differently than it was done in lecture, and that's just because we'll come back to the way we did it in lecture in a bit, but let's suppose that the correct class for y is 1. Okay, so this table, it is a first state. So for a binary classifier, the KL divergence is simply the log of 1 over our prediction value. So for example, if our table is actually a first state, that is, the correct class is 1, and our prediction, like our model, says that it's a first state with 57.7% confidence, then the KL divergence is log of 1 over 0.577. That's what we gave it. That's would give us a value of 0.239, and we could think of this as the loss. Now, the best possible prediction we could make is to say it's a first state with 100% confidence, and we will be rewarded in that sense with a loss of 0, because the log of 1 over 1 is the log of 1, which is 0. Okay, so basically, the closer our prediction is to 1, or 100%, the lower our loss is. And if our KL divergence, if we gave it a 0% chance, then our KL divergence would be very large. It would run off to infinity. All right, so here, in case you're, oh, actually, if we want to do this again from scratch, a different way of looking at that is, well, we know what this expression is right here. We know that we have it on the previous slide. So the probability, our estimated probability that it belongs to 1 is this expression. So if we do 1 over that expression and take the log, it ends up being, if you just substitute in, it's log 1 plus e to the minus phi transpose theta. And so we could plug in the actual numbers again if you wanted to do it instead. So if you want to work out from scratch, just using the dot product itself, well, here's the math, basically. You again compute the value of 0.312, and the log of 1 plus e to the minus 0.312 is 0.239. Okay? And so you can think of this as a loss, and again, this value can vary anywhere between 0 and infinity for a single data point. On the other hand, if the correct class is in fact 0, well, in that case, the KL divergence is just log of 1 over the probability that y is 0, and that, of course, the probability that our model predicts that y is 0 will just be 1 minus what our model predicts for the class being 1. Okay, so basically the KL divergence, there's two cases. The correct class is 1, the correct class is 0, and we have pretty simple expressions for both. We could also give one single expression that covers both cases, where we just say, okay, well, the total loss for a given data point is, well, we have an indicator function, so we say if the actual class is 0, then we use this expression. Otherwise, if the actual class is 1, we use this expression. And this indicator function allows us to basically take those two cases and combine them into one single sum. Okay? Now, this may look quite different than what you remember from lecture. This should have seemed unfamiliar. But the reason I did it this way is to more carefully draw out the important ideas. This is the KL divergence. But in class, we had this other seemingly much more complicated expression that we started from. So where did this thing in class come from? Well, it's just an observation that we can generalize this idea here to multiple classes. So if we wanted to, say we had 5 classes, we would just say, okay, well, the total loss would be, we figure out which case we actually are. So whatever the actual class is for y, the indicator function picks that one up, and it's just 1 over the probability that our model says that the correct class is k. All right? So this is a more general way of writing this if we had multiple classes. And that brings us to what we did in lecture at the very beginning when we introduced KL divergence, where we said the KL divergence for two probability distributions, P and P hat theta, right, or just any two, is going to be, okay, this may look quite different than this right here, but it says they P of y equals k given x, both to the left of my log and on top, and then at the bottom in the denominator we have p hat. So what's going on? Why is this expression the same as this one? Well, keep in mind that when we're doing this analysis, that the actual probabilities, these capital P's, we have concrete observations. So that is, we know, like I have a specific table and I know for a fact that in my training set, this was an actual first date. And so this value is always going to be either 1 or 0, hence the indicator. And so this we could think of as just an indicator function. And in the numerator, well, since I already have an indicator function over here, I just put 1 for simplicity. And then down here, I still have p hat theta. Okay. And so to make that a little more clear, there is a general idea that goes far beyond the scope of our class, and this is the definition of the KL divergence. And in our specific case, in our course, where we have concrete observations and predicted probabilities here for the class, in that case, this expression basically just reduces to what we have on top. Okay, so different way of thinking about KL divergence. This is a review, so if this didn't really make sense, you should definitely go back to the original lecture, because I just wanted to cover things that hopefully you already are kind of familiar with from a slightly different perspective. All right, so to wrap this up, there's a little more, but to wrap up the idea of logistic regression, assuming we have just two cases, which is what we are going to do in our class, the average loss across many data points will be 1 over n times the sum over all of our data points, and here I'm subscripting y with an I to indicate the ith data point, and that is now taking into account all of our data points. And in this case, p hat theta, of course, is just what we said before. All right, so how do we minimize this, right? So if we want to actually minimize this loss, then minimizing this loss, and this is something I'm skipping a bunch of math, but minimizing this loss is the equivalent of minimizing this expression. So here, I won't go into any of the details, but there was just a bunch of algebra we did in calculus and basically said, okay, minimizing this whole expression basically boils down to this one, but I'll skip that derivation in this review lecture. Okay, now we had this issue, which is that if we have data that is linearly separable, that is, let's go back to this example we had before. Linear separable would mean that there is an actual line that does a perfect job. So here there is no line that does a perfect job, but if you have data where there is a line that does a perfect job, you have an issue that the optimizing parameters, that is the thetas, they become infinite. And another way of putting it is that means that your model now has extreme overconfidence. It's going to say for every point in the space, it has probability either 0 or 1. And that is not great, right? To have a model that's just that confident. You want to ideally have a model that's a little more realistic. And so we can fix that by using regularization, just like we did with regression. So in particular, we have our original expression we're trying to minimize, and then we add this term over here. This would be for ridge regression. But in general, if we had another regularization function, we would replace it with lambda r theta. Now this expression, if we actually want to minimize it, unlike the normal equation for linear regression, there is no closed form solution for this, and so we need to use something like gradient descent to optimize this expression. Okay. So to basically summarize that entire couple of lectures, and this was the most mathematically challenging, I think, of the whole semester, in linear regression, we wanted to minimize this expression. So we wanted to find the theta that minimizes this expression. And in logistic regression, when we want to build a classifier, we use this expression at the bottom instead. So basically, ultimately everything in that lecture boils down to, for regression, we use this expression. For logistic regression, we use this expression. As a side note, as I just mentioned, the top expression here can be solved using the normal equation, but this bottom one, we have to use a numerical method. So now, just to compare them side by side, I said at the beginning that linear regression is overly sensitive to outliers. So here what I'm showing you is, as opposed to before when we did a linear regression model and drew a least squares decision boundary, where this is the 50% mark for the yellow regression line we are not showing on this figure, the logistic regression is a little bit to the left. And if we looked at the actual errors on this data, this one would be a little lower in terms of the error rate. But actually, that's not the important part. The really important part is that if we now add an extreme point way out there, so I'm showing, remember that value that was 100 out there? Now, if we look at the logistic version of our logistic regression here, it barely moves its decision boundary in response to that extreme point, whereas the least squares boundary moves quite a lot. And so this is more robust to outliers, and thus it makes for a much better classifier. Okay, so that's logistic regression in a nutshell. I hope that was helpful to see it from this slightly different perspective and not confusing. And so, yeah, we'll move on from here. This, I think, will be a little more straightforward. But this, I think, is one of the most mathematically challenging lectures. And this particular review section is going to be certainly the longest as a result. So I'll see you in the next video.